Okay, guys, we're back. Looks like you can hear me. I'm at my house again. Check it out. Back at my house. It's like 11 at night. Everyone's sleeping. No, actually, I'm lying. Only my wife is sleeping and my youngest son. The girls are both still up. So I'm down in the basement, trying not to be too loud. Teach you these notes. So I have to take my daughter to the doctor. So I didn't get out of it. So I'm not there today. So hopefully you're watching this. So here's your warm up. Go for it. Pause the video right now. Do the warm up and then unpause it and watch me do it. Okay? Go for it. Hit pause. Okay. Pause is over. You just finished. Okay, so let's do the problem. Undo that. So this is what we did today. CDC reports 22% of 18-year-old women in the United States have body. So they just gave you the true answer right there, okay, for the population. And at a local college, a health clinic had 200 randomly selected. Oh, so that's great. Randomly selected. Female students report their heights and weights so that the BMI can be calculated. Only 31 of those students had body mass indexes greater than 25. So only 31 were higher than 25. So the proportion they got, p hat, in our sample was 31 out of 200, which is not particularly high. I can't move my mouse over there. Hold on. I don't have my mouse with me. I didn't bring it home. Okay, I'll put it there. So 31 divided by 200 puts us at a percentage of 15.5%. So this college had 15.5%. Okay. Is that proportion unusually small if the true percentage is 22%? Well, if let's see, we did a sample of 200, okay? So if we did a sample of 200, then to have the central limit theorem work, right, our conditions have to be met. We had a random sample. They told you they took a random sample of 200 female students. And then 200 has to be less than 10%, so they better have more than 2,000 female students, is less than 10% of female students at their school. And then do we have enough, do we have a large enough sample? Well, only way we know is to do 200 times our true value of 22% and 200 times the opposite, which would be 78%. So when we do 200 times those, obviously, you know these are going to be bigger. 44 for that one. And the other one's going to be even bigger, but you still got to do it. 156. So both of those are bigger than 10. So our sample is large enough, so that means we have a normal model. So I now know that a normal model is formed. So you don't have to sketch it, you guys. I'm going to sketch it because you're watching this. Ooh, that was a good one. Only a little bit right skewed. I'm happy with that one. I'm happy with that one. Okay, so the middle of this model is our 22% that we think is the true answer, and our standard deviation would be the square root of 22% times 78% divided by the 200, which I have a feeling this is going to be fairly small. So 22% times 78% divided by 200, and then don't forget you need to square root that. So this 0.0293. 0.0293. So about 3% almost. So that's not that big of a change, 3%. So is 15% unusual? Well, it's somewhere out here. Is that unusually small? Two ways you can back up your data. You can find the area of that region below that point and give me that probability if you want. Okay, that right there, right, is your normal Cdf probability. You could do that. That's more work than you have to do. My lower limit is going to be 0. My upper limit will be the 15.5%. Your mean is going to be the 22%. And the standard deviation was 0.0293. So you could do that. That's one way to get some kind of support for my answer. 0 to 0.155, and you're going to go 0.22 is the middle, and 0.0293, and that's going to give you, oh, did it twice. Why did they give me different answers? No, they didn't. Oh, 0.0133. 0.0133. So that, not going to happen. Seems unusual. Another way to show unusual, so one way is to say, oh, look at how small that percentage is. We would only have about a 1% chance of that happening. Or you can do your z-score. Because, right, if you're more than 2 standard deviations, that's pretty far. So 0.155 minus the mean divided by the standard deviation. So that is another way you can show something is unusual. Just figure out what the z-score is. There's the top divided by 0.0293, and we get negative 2.21. That's pretty good. Probably 2.2 when I round it. So that's also shows you that it's unusual. So your answer to this problem is not those numbers. Your answer to this problem, is it unusually small? Yes, because there's only a 1% chance that happens. Or you could say yes, because it's more than 2 standard deviations below the mean of 22%. Okay, so that's pretty unusual when we're looking at the grand scheme of things here. On what this is our model because the central limit theorem was met. So that would tell us that this is our model, okay, for what happens, right, when you do a sample of 200 people. This is what will happen, okay? So 15%, pretty unusual. So this school is obviously unusually small amount of BMI, high BMIs. So there's your warm up. Okay, so today, for you guys yesterday, we had just started on the means. Central limit theorem still valid as long as conditions are met. We learned that the middle is the true mean of the population. It is a normal model. Okay, so just like the proportions were normal, the averages will be also normal. And the standard deviation, little different formula. The standard deviation is sigma, which is the standard deviation of the population divided by the square root of the sample size. That is a big deal. We will use it a lot when we get to chapters 23 to 25. Okay, so we need to talk about conditions for meeting, okay, using the central limit theorem. So first condition, still random sample. And the reason that's a condition, right, remember the first two conditions are to help us have independence, right? It's helping us show that our probability doesn't change as we go through the process. So random sampling, or maybe they did an experiment, so you did random assignment. So I don't know, but it's some kind of randomness. And then your sample size is less than 10%. Is less than 10% of population size. So those two don't change. Same conditions that we had on the yesterday. So that's not changing. Okay, the third one is the change. This is a little different. So we can actually, okay, so remember the proportions, it was you have to have 10 successes and 10 failures. And so you know you're going to have a fairly big sample because it's hard to get 10 successes and 10 failures when you do n times p if your n is not fairly big. Okay, right? Because what if your proportion is only 10%? Well, then I got to have at least 100 as my sample size. So it's hard to use small sample sizes on proportions, right? You're not going to see a lot of small sample sizes on proportions that will check out on that condition. Okay, if we go back to that condition, right? We're not going to have a lot. N is going to be fairly big if we're going to have 10 successes and 10 failures. Okay, N is going to be fairly big. So probably, right, depending on what the P value is, and probably small. You're not going to see usually much smaller than like 20, right? Because if it was 20 times 50% would be 10. So that's like the smallest you could really have N is like 20. So you will never see something probably smaller than 20. So that doesn't happen on means. Means are different. So on means, you can have you can have more variety on your sample. You could have 2. That would be okay. You could have 5. You could have 10. So you won't see those on proportions, but on means you will. So I have some different criteria. The condition is actually called the nearly normal condition. Actually, no, let's not call it that. We'll save that for later. Let's just call it large enough sample. So that's the condition. How do we check it? Well, it changes. If the population is normal, right? So the population looks like a bell-shaped curve. So if you looked at the population of like all of Westland High School students' GPAs and it looks like this, then you can take any size you want. 2 is fine. 3 is fine. 4 is fine, right? Any size you want. So if the population is normal, any size is good. Well, what if the population is not normal? What if the population has a slight skew? Because that's pretty common. So if the population has a slight skew, like not a really big skew, just a slight skew. Okay, if the population has a slight skew, you got a little right skew, a little left skew, then we want a slightly bigger sample to help sort of negate that. So probably we would like to have a sample size bigger than 10. Now these are just rough, these are not exact numbers, right? If your sample size was 8 or 9, I'd probably be okay. It's just like it's around 10, right? We're looking for something around 10. If they had a sample size of 2 or 3 with a population that has a slight skew, it's not good enough, okay? And then if the population has a large skew, or there are outliers, right? Outliers are unusual. Sometimes they might come up in your sample. So if the population is weird, large skew, outliers, then our sample size should probably be above 30. Now, again, it's not a hard line. We say 30. I've seen some books say 25. So 25 to 30, right? 10 is not big enough. 15 is not big enough. 28, probably okay. 25, probably okay. 40, even better, right? So that's sort of, so you have different cases here. So sometimes 2 is big enough. Sometimes 2 is not big enough. Sometimes 10 is big enough. Sometimes it's not. And sometimes the only thing big enough will be 30 or more. So these are what need to happen. Why? Okay. Why? It's all because of yesterday when I showed you that applet about calculating the mean. When you didn't take a big enough sample, it won't get normal looking. It's one of the conditions. So let me put in sampling distribution applet. No, not that one. That's not it. Okay, so this is the one. So I want to show you, right? Okay, so see if the population is normal, I could do a sample size of 2. Animate it. 1, 2. There's the mean. 1, 2. There's the mean, right? And now I do that 10,000 times. Okay, do it 10,000 more times, right? Do it infinite times. There's 100,000. It looks pretty normal. Okay, it looks great, right? It looks normal, just like the original looked normal. What's the only difference? Well, the difference is the standard deviation is a little smaller when we did a group of 2. And found an average of 2 people from the population. Then our standard deviation is 3.5. The original standard deviation was 5. So that's our formula that I gave you. It goes down a little bit because you got to divide by the square root of n. So see, it's okay. But if this had been skewed, and I picked a sample of 2, and I just keep doing that, and I do that 10,000 times, and another 10,000, right? Now I'm up to 100,000. I wasn't able to make it look normal. I did 110,000 different samples. It doesn't look normal. It still has a right skew. So see, 2 was not big enough when we had a skew. This is a pretty heavy skew. So 10 might be big enough. Let's see. It's getting there. It still had a little skew, but it's not terrible. You see why it's not a rough line. 16 might be a little better. 20 would be probably better. Still a tiny skew, but looks a lot more normal. See, so this was a fairly heavy right skew. So, I would have probably felt safer the closer to 25 I was, right? That looks fairly normal. So see, if the population looks weird, then weird things got to happen. Like, what if I just had like a population like this? This is a weird one. This one, I'm going to put some with outliers. Come on, why don't you go on there, outliers? Outliers, right? Let's take 2 again. That doesn't look good. And look at that. I did 110,000 times. That doesn't look close to normal because I only took 2 in my sample. See, the outliers messed that up. Well, this one, let's try 10. Let's see what happens. Trend 10 people from there. Find the average. Boop. Do it again, do it again, do it again. 10,000 times. Look how much better that one is. So you see that one's getting better, but it's still maybe a little right skew. So this was maybe I want to go to like 25. It should be fine on 25, right? Pretty good. Okay, pretty normal looking. It's not perfect, but it's pretty normal looking. So the outliers weren't able to affect it when we picked 25 out. Because, right, then you don't just have one outlier show up. When you're only picking two, what if the two that you got were this one and this one, right? That's a weird number. It's going to look weird. Okay, so even when you find the average of these two, it's going to be way over here. So that's the danger when you have a weird population, is you got to pick more. So when you find the average of 25 of them, they're all basically in the middle. So that's what we mean on the sample size. Sample size depends on what the population looks like. So it's a little weirder than the proportions, because on proportions you just did 10 successes, 10 failures. You didn't worry about it anymore. This one you have to think more. It's not any work. You just have to think more. And you have to say your answer depends on what you're told or what you can think about when you think about the population. So that's it. Those are your checks for your conditions. If these are all met, then we know that a normal model is okay. Okay, with the standard deviation of sigma divided by square root of n, and the middle will be the true mean of the population. There we go. Okay, if these conditions are met. That's it, you guys. That's what I had to teach you today. The rest of the stuff is examples. So pause it, try and do it yourself, unpause it, and watch me do it. Okay, stop now. I'm frozen. Okay, I'm unfrozen. Okay, Centers for Disease Control. Here we go. Mean weight of adult men in the United States is 190. The standard deviation of 59. So they just told you the true mean is 190 pounds. I feel really good now because I'm below that. And the true standard deviation is 59 pounds. Okay. An elevator in our building has a weight limit of 10 persons or 2,500 pounds. What's the probability that if 10 men get on the elevator, they will overload the weight limit? Well, what would be the average if 10 men got on that elevator that would be too big? The average weight of each man would have to be 250. So we would like to find out if we will have an average greater than 250 when 10 men get on this elevator. Okay, so we got to think about this. Well, I'm taking a sample of 10 men. So conditions, random sample of 10 men. Right? The 10 men that get on an elevator, they don't probably know each other. Probably 10 different men, can be seen as a random group. So hopefully no brothers, sisters, relatives, dads, right? Brothers, right? That kind of stuff. Because they might be overweight together. Random sample of 10 men. 10 is way less than 10% of population size. And then your third condition, right, is, okay, is that big enough? Is 10 big enough? Well, weight, I think weight tends to be normally distributed. Maybe in the United States, we might have a little bit of an obesity problem. So maybe we have a slight right skew. So anything a slight right skew, but I sort of think normal. So I think 10 is a big enough sample. And I'm going to say because weight is probably normal. Normally distributed or only slightly skewed. I would think it would be slightly less skewed. Sorry, right skewed. We might have some few people that are really overweight. So slightly right skewed, 10 is fine. So there's my conditions. They're all met, which means I have a normal model. And our normal model I like to draw it on the problems on your homework. They will have you draw it on a few of them. So we're going to draw it, right? And the middle is the true average. So that true average is 190, okay? This is representing the average weight of the men, okay? The standard deviation, that doesn't even look like 190. That looks terrible. I gotta erase that, that's bothering me. So that's 190. The standard deviation will end up being the standard deviation of the population. So 59 was the population. When I pick 10 people on and take their average of the 10 people together, it's going to be a smaller standard deviation because it's harder to be an extreme number when you're taking 10 people. So 59 divided by the square root of 10, and there is your standard deviation now. And it's not 59 anymore. When you take 10 men and you find their average, it's now 18.66. So that's the new standard deviation. So this one is not quite as big, right, as this one would have been, okay, when you only picked one person. So now you'd subtract 18.66, so the next one is like 190 minus 18, or 9, let's just 190 minus 170 would be 20. So like 171-ish right there, right? Next one would be about 161, 151, about 152-ish. I'm not exact, right? I'm trying to get this quickly for you guys. And then if you go above, right, the next one would be about 200, 210, about 209, close to that, 208.66. The next one would be about 19 more than that, 219, 229, 228. And the third standard deviation, 238, 248, 247, around that. So these are rough numbers, okay? So that's what will happen when we take 10 people and find their average. Are we going to get 250? Probably not. Look how far out 250 is. So probably not. So they asked us did they ask us what the probability is? What's the probability 10 men and they will overload? So they want to basically asking you, what's the probability our average is bigger than 10? That little thing right there. So those of you who use the z-score, calculate the z-score. Remember, I don't like to do that. I like to use Normalcdf. The upper limit, we got to do an infinity again, not 1 anymore. These aren't proportions. And you're going to go, the mean is 190, and the standard deviation for the new sample is 18.66. Don't put 59 in there. You will get a wrong answer, right, if you put 59 in there. So Normalcdf, and you're going to put in the numbers 250, infinity 1, e 99th, and then it's 190 and 18.66. And you get, wow, small number, 6.5 times 10 to the negative fourth. 6.51 times 10 to the negative fourth. Tiny, right? That's the probability that we get an average weight of over 250 when 10 men get on there. Probably not going to be overloaded, okay? Probably not going to happen. It was over 3 standard deviations above the mean, okay? It'd be really hard to get an average for 10 men that's 250 or higher. One man, easy, right? One man, easy. You pick one man, 190 is the middle, but the standard deviation is 59. So 250 is actually not that far away when you're only picking one person, right? Because that's what happens when you pick one person. But if you're picking 10 people, the standard deviation totally changes, and it's not easy to get 250 for an average of the 10 people, okay? Pay attention to that for the quiz, okay? Pay attention to that for the quiz. So I have two other problems on these. I'm trying to remember which ones are the better ones. They're basically all normal CDF calculations. So again, pause it, try and do it, and then come back and watch it. Okay, so we're at 29 minutes right now. Pause it. Okay, you're back. Here we go. So part A. Assume that the duration of human pregnancies can be described by a normal model with a mean of 266. So that's for one woman. The mean is 266. Whoa, why did I do one? And the standard deviation is 16 days. So that's for one woman then. What percentage of pregnancies last between 270 and 280? So basically, they're asking you for, if you just pick one random woman, and you know that it's 266 for the middle, and the standard deviation is 16, what's the probability that your pregnancy will be between 270 and 280? They basically are asking you for that right there. So if you're going to do this with z-scores, you guys, it's going to be hard. You're going to have to do two z-scores. Look up both areas in the table and subtract them. That is harder to do. This is why I hope you don't do that. I hope you use normal CDF and you go lower limit. I love these ones. 270, upper limit, 280, mean, 266, standard deviation, 16. Pretty straightforward, okay? Pretty straightforward. So normal CDF, let me move it to the other side so I can see it. We're going to go 270. I love these ones. You don't have to put infinity in. 280, 266, and 16. 21% chance, 0.2105. 2105. There you go. There is A. Probability that if we pick one person at random and their pregnancy lasts between 270 and 280, about a 21% chance. Okay, part B says, at least how many days should the longest 25% of pregnancies last? Same model, picking one person at random. If you were in the upper 25%, how long would your pregnancy have lasted to be in the upper 25%? Well, still 266 in the middle. Standard deviation is still 16. We want to know the upper quartile, basically. So we'd like to know, where is that Q3? And what is it? We know the area over here should be 25%. So I don't know, it's been a long time since first quarter when you guys probably did this. This is your inverse norm if you've forgotten. Inverse norm. And remember, your calculator depends on what operating system you have. If you have the newer operating system, you can put in the area on the right and put in 25%. If you have the old operating system, all you can do is left. You don't have a choice. So I'm going to practice people with the old operating system. I'm going to put in 0.75 for the area on the left. The mean is 266, and the standard deviation is 16. And that is the area on the left, and it will then tell you, voila, Q3. So I did 0.75 for the area, I did a mean of 266, and I did a standard deviation of 16, and that just told us that that number was 276.8 days, right? So if your pregnancy lasts more than 276.8 days, you are in the upper quartile. Okay, so 277 basically is the upper quartile. So right now you're thinking, Mr. Shelvin, Why is this in this chapter? Because those are basically chapter 6 problems regurgitated. Yes, those are chapter 6 problems regurgitated. So finally in part C, we get to the current stuff. Suppose a certain OB is currently providing prenatal care to 60 pregnant women at their clinic. Let Y bar represent the mean length of those 60 women. According to the central limit theorem, what's the distribution? Specify the model mean standard deviation. Okay, so if the conditions are met, then it would be a normal model. So let's think about our conditions. Well, I'm hoping these 60 women they're like 60 random women that go to this OB. Right? They're not related. They just found this OB and they're just random women, right? Independent of each other. And then 60 is less than 10% of all pregnant women. Way less. And 60 is a huge sample. So it doesn't even matter. We already know that pregnancy is normal because they told us the human duration of pregnancies is normal. We already know it's normal. So we could have had a sample of 2 and I would have been happy. They did a sample of 6. 60 is more than large enough. With a normal population. More than large enough. I would have been happy with 2. So 60 is awesome. Way bigger. We didn't have to worry about it. They could have told you nothing about the population and you still would have been happy because 60 was greater than 30. So you still would have been happy. So we now know that the central limit theorem does apply. A normal model is created if you do an average of these 60 women. The middle will be the same middle as the one for one woman, 266, but the standard deviation is no longer 16 when you take an average of 60 women. The new standard deviation is 16 divided by the square root of 60. So that is the new standard deviation. You have to change that. They will get you on a test question because you'll forget to change it. 2.066. 2.066. So, right, this is the new standard deviation. So it's not as wide because now it's like 268 right there. Now it's like 270. This side, right, 264, 262, right? Totally different than this one when you were going by 16. Totally different when you're taking a group of 60 women and finding the average for those 60 women. So there's the model. You got the mean, you got the standard deviation, you're done. That is the model. Part D, what's the probability that the mean of these 60 patients is less than 260? So you don't really need to do another drawing. They're basically asking you that the mean is less than 260. What is the probability of that occurring? Well, I'm not a z-score person. I'm a calculator person. So I'm going to do normal CDF, right? And you can put your lower limit as 0, be totally fine. Upper limit is going to be 260. Your mean is going to be 266. And your standard deviation is now 2.066, not 16. And I guarantee you, if this is a multiple choice test, they have the answer that you get when you put in 16. That will be there on the thing. You could put in negative infinity. You could put in 0. I don't think it will change our answer. I'll check, just to make sure, but I really don't think it will change the answer. 2.066. And wow, 0.0018. It's tiny, tiny. The probability we get an average for these 60 women less than 260 is tiny. Let's see if it changes my answer. I'm just going to play. I'm just playing here. Does my answer change if I put negative infinity? E to the 99th. Let's see if the answer changes. No, didn't matter. So see, 0 was fine. But I guarantee you, if I'm making a multiple choice test and I'm an AP exam maker, I'm not, but if I was, I would be putting in 16 here, and I'm going to figure out what that answer is, because I would definitely be putting that answer on the test. And I bet half of the students will pick that answer, 0.3538, because they will forget that when you take a group of 60, the standard deviation has to change, right? You can't get as much variation when you have a 60 and you're finding the average of 60. That's not going to vary as much as one person, just picking one person at random. There you go. That is it. So that's sort of what you're going to do on homework. So you're going to do normal CDF again on homework. Same stuff as what you've done before. That's 40 minutes, exactly what I thought it would take. It's now midnight in my house. And you think like I'm wide awake, ready to party all night long. Okay? So, you know, let's start the DJ music. I don't even have my right soundboard on. Man. So there we go. Party all night. Party all night. Let's turn on the voice changer just so we can party. Not that one, not that one. I picked the wrong one. Sorry, guys. If you're still watching this video right now, you just lucked out. It's a little out of sync, but there you go. Enjoy it. Enjoy it. Enjoy it. Go do your homework. Go do your homework. Go do your homework. Go do your homework. Okay, guys, I'll stop. I'll stop. We'll turn off the recording. We'll see you guys. Do your homework. We'll go over it tomorrow. Maybe we'll get a quiz in. We probably won't get a quiz in. I'm just saying the quiz will probably be Monday. That's it. Have a good rest of your day.